All right, in this lecture, we will discuss your chapter number 12, which is probability. You already know a little bit of probability. It's not just a little bit, actually. We have discussed all the important probability distributions. So it's a fairly strong foundation you have about probability. And you also know how to identify the random variables and what are the random variables, types of random variables such as discrete and continuous and so on, and what are the probability distributions that are classified under each of these two cases. And also how to write down the probability statements such as probability x equals k and probability x is lesser than or equal to k and probability of x is greater than or equal to k and so on, right? Probability of x is between k1 and k2. So those are the probability statements and you know how to write them down. But also there are a few other simple theorems you should know before moving into the proper data analysis stage. So the probability distributions will give you the probabilities. But on the other hand, there are some equations that are important, okay? So we will see those equations in this chapter. Of course, there are two types of probabilities you're going to see. One probability is the probability of a given event, like this. Now this A could be your random variable x is lesser than or equal to 12, for example, okay? So these kinds of probabilities will be discussed in this chapter. Well, they're just probabilities, and I will still label it as simple probabilities. They're very easy to understand, so I will just call it the simple probabilities. And under your next chapter, which is chapter 13, which is an optional chapter, but we will discuss that one in this intro statistics class. And there's another type of probability. That is called the conditional probabilities. Is there a way that I can improve the probability of a given event when I have information about a related other event? Let's say I have two events, A and B. And is there a way that I can write down the probability of one event given the probability of another event? So these kinds of probabilities are called conditional probabilities. The conditional probabilities will be properly defined when we discuss your next chapter. So at this point of time, if you cannot understand this notation, just don't worry, okay? You don't need that one to understand chapter 12. So in chapter 12, we will only look at the simple probabilities just like this. And then, as usual, I have posted this lecture note on Canvas, so please go ahead and download that, and then you can watch the lecture and fill the blanks with me. Under point number 1, I have defined random experiments because the probabilities are actually defined for random experiments. Now, what are the random experiments? Well, random experiments are the cases where the outcome is a random variable. We already know what are the random variables, okay? We have discrete random variables, continuous random variables, and so on. So any experimental setup which provides you a random variable as the outcome, or the response variable, is called a random experiment. So we define the probabilities for those random experiments. So here are some examples. Think about rolling a die. So if you are going to roll a die, what are the possible outcomes? The outcomes are 1, 2, 3, 4, 5, 6. That is, if your die has 6 sides, okay? So these are the possible outcomes. And think about the next example given, observing the number of vehicles entering the campus parking during weekdays. Number of vehicles entering the parking lot. Now, what are the possible outcomes for that? Well, this symbol is used for number of, okay? So the possible outcomes could be maybe 0. You know, it's a possible value. And it can be 1, can be 2, 3, and so on. And there's no specific upper limit other than the complete capacity of the parking lot. And then measuring the rain, for example. We will measure rain. If you measure rain So what are the possible outcomes? Well, now it's going to be a continuous random variable. So possible outcomes could be all the values from 0, and we don't know the upper limit. So we'll just write 0 to infinity and write it as an open parenthesis, because infinity is not a real number. So this is going to indicate all possible outcomes of that. And then measuring the temperature of a surface. Temperature of a surface, measure temperature. Of course, we know that the temperature can be negative and it can be positive. So it's another random experiment. You're going to measure the temperature, and possible outcomes may be from negative infinity to positive infinity. All the values are theoretically possible. So that will also be a continuous random variable. The first two examples are examples for discrete random variables, and therefore they are experiments regarding discrete random variables. And then the next one is measuring the tensile strength of polypropylene fiber. So the tensile strength measurement. Measure tensile strength of some material. In that example, polypropylene fiber. It will never be equal to 0, but practical values, theoretical practical values from 0 to positive infinity. Okay. I'm writing these as interval notations, which you must have discussed under college algebra. All right, so these are some examples. They are written down under point number 1. They are called random experiments, and we define the probabilities for these kinds of random experiments. Okay. All right, let's move on to point number 2, the sample space. Now, what is the sample space? The sample space is defined as all possible outcomes of a random variable. Or you can also say all possible outcomes of a random experiment. Either way is fine. So the point number 2, sample space. We said it's all possible outcomes. Of a random experiment. The sample space has a symbol. So the symbol for sample space in this class will be S. Many other statistical literature also people use sample space is S. But there are a few other symbols also you will see if you read a statistical paper anywhere. One other symbol is omega, uppercase omega for sample space. And also sometimes you will see epsilon used for sample space. But for this class, we'll only use S for the sample space. Okay? So the sample space for the first random experiment, rolling a die, if it has 6 sides, this is my sample space. Okay? So number of vehicles entering a parking lot. This is the sample space, so this will be my S for that experiment. Okay? And measure the rain. So the height of the rain could be from 0 to positive infinity, and that's my sample space for that experiment. Measure the temperature of a surface. It could be anywhere between negative infinity and positive infinity, so that's my theoretical sample space for that random experiment. Okay? Measure the tensile strength, so it could be anywhere between 0 and positive infinity for theoretical purposes. So the sample space in that experiment is that. Okay? So always we write sample space as that. All possible outcomes of an experiment, and we write it as uppercase S. All right, and then point number 3, the events. Events are defined as any subsets of the sample space. I would say any subsets of S. We have already defined S. Okay. So any subsets of S can be considered as events. Events are usually given by letters A, B, C, and so on. And if you have a fairly large number of events, you can write them as A sub 1, A sub 2, A sub 3, and so on. Or maybe B sub 1, B sub 2, B sub 3, and so on. Okay? When I say subsets of S, this also includes two special subsets. One is the sample space itself. So I would say including S, which is a sample space, and also the null set or the empty set, which is the set which does not have any elements. It's written as just two curly brackets without any elements inside. That's one way to write it. Also, you write it as a little 0 and cross that. Read as phi. So that's the empty set. So including these two, any subset of S can be considered an event. So one example for an event for the first experiment right here is, let's say, A equals receiving an odd number. So it's 1, 3, 5. It's an example for an event. Also S itself, including all of these numbers, will also be considered as an event. Okay, good. Let's move on to point number 4, probabilities of events. Now that's very important. Number 4, probabilities of events. All right, we said sample space itself is also an event. So the sample space is, that has a probability of 1. So the probability of the sample space is taken as 1 always. Please remember that, that's very important. And the next point is the probability of the null set. Null set, which can be written as a 0 and a little vertical line, or you can write it as a 2 curly brackets without any elements inside. So that's the null set. So the probability of the null set, what could be the probability of the null set? This is equal to 0. Okay? So any other set will be between these two. Okay? Any other set can be considered larger than the null set and larger than or equal to the null set to be theoretically correct, and smaller than or equal to the sample space. Okay? So let A be any other set. Defined in the sample space S. The probability of the event A will be between 0 and 1. Now this is extremely important to remember. As a probability, if you ever write an answer which is larger than 1 or which is negative, your answer is incorrect. Always, the probability of any event should exist between 0 and 1. So whether you have to write them as decimals or convert into percentage, it's up to you. If you like to keep it as decimals, keep them as decimals. If you would like to convert them into percentages, convert them into percentages. That's up to you. Both formats are accepted in the homework and in the exams. Okay, good. Now, let's move on to point number 5. So how do we determine some of these probabilities? Well, there are popular methods of determining probabilities. We will just discuss 3 methods of determining the probabilities. The first one is called the classical method. The second one is called the statistical probability. The third one is called the judgmental probability. Now let's look at these 3 cases. under point 5. The first one is the classical probability. We use the classical probability when all the outcomes of an experiment are equally likely. That means we use the uniform distribution. Okay? So I will write it down. Used when all the events are equally likely. Okay, so practically we are using the uniform distribution. This could be the discrete uniform distribution, or it could be the continuous uniform distribution. Now, for example, think about rolling an unbiased die. The outcomes are equally likely. Sample space is 1, 2, 3, 4, 5, 6. I need a probability distribution. Let's say these are my x values, 1, 2, 3, 4, 5, 6, and in the next line I need to write down the probability that x is equal to each of these values. And in general, I will label this row as probability x equals k. So when k is equal to 1, I have 1/6 as the probability. When k is equal to 2, I have 1/6 as the probability. 1/6 again, 1/6 again, 1/6 again, and 1/6 again. Okay? So this is the discrete uniform distribution. Another example could be the solar radiation during summer times. So that may follow a uniform distribution between two given values. Solar radiation during summer. Let's say this is between 5 and 7.5 from whatever the units used to measure the solar radiation. Now this is a continuous random variable. That means, now here's our distribution starting from 5 and go up to 7.5. And I can define this vertical height. We need to make sure that this total area is equal to 1 unit. So this length is 7.5 minus 5, which is 2.5. So the vertical height should be 1 over 2.5. So that the area of this rectangle, which is this side times the other side, is equal to 1 unit. Because we need the total probability to be equal to 1 unit. When, if you look at the previous example, 1/6 is added 6 times, which means the total probability is equal to 1 unit. Okay? So that's that classical probability. When the outcomes are equally likely, we go for the classical probability using the uniform probability distribution. All right, so the next one is the statistical probability. We go for the statistical probability when the outcomes of an experiment are not all equally likely. Okay? So I write it as that. When the outcomes of an experiment or of the random variable, when the outcomes are not equally likely. Just because the outcomes are not equally likely, we cannot simply go for statistical probability unless you have the past data. If you have the past data, we can figure out a probability distribution which will be different from the uniform distribution. So there's that second requirement. The past data are available. So that we can figure out the probability distribution. Okay? Statistical probability means we're going to use a distribution which is other than the uniform distribution. Okay? So past data are available so that the distribution can be determined. So one example could be, if you need a discrete example, rolling a biased die. Okay, rolling a biased die. The outcomes are still 1, 2, 3, 4, 5, 6, but the problem is they are not all equally likely. In that case, I cannot use the discrete uniform distribution. Another example could be number of vehicles entering a parking lot. That will definitely never be equally likely. We are not going to use any uniform distributions in these cases. Often we go for the Poisson distribution with a certain rate, okay? Hourly number of vehicles or daily number of vehicles. That's the parameter for the Poisson distribution. All right, so these are some examples for the discrete random variables, and we can also have continuous random variables. Heights of people, for example. It will be a normal distribution. Most of the people will be around a certain height. Number of really tall people will be low. Number of really short people will also be low. That means we'll have a nice symmetric bell curve with lesser number of frequencies towards the tails. Okay? So in such cases, if you have past data, we can figure out the probability distribution. So we call them the statistical probability. There's another way to estimate the probability. When these things don't work, that means if the classical probability fails, we see if we can go for the statistical probability. But in case if I don't have past data maybe, or maybe a scenario which is not so compatible with statistical probability, in that case, we will have to go for another third category of calculating the probability. It's called the judgmental probability. Now we go for the judgmental probability when the classical and statistical probabilities are not going to work. Okay? This is when classical, which means the uniform distribution, or statistical, which means all the other distributions, methods fail. And the past data may not be available, or the available past data may not be relevant. Well, in that case, how shall we figure out the probability for a certain event? Now, what are the possible examples for these situations? Think about a major surgery and probability of survival after that. Or think about a certain cancer and 5-year survival rate. Well, of course, for a cancer 5-year survival rate, maybe the past data are available. But on the other hand, the past data alone may not be that relevant, because 5-year survival may depend on various factors. The age of the patient, physical fitness of the patient, whether he had some other conditions such as heart attacks and so on, whether the patient was a smoker or not, it may have some impact on the final result, and so on. There can be so many other related factors. Survival after a surgery, or recovery, rate of recovery after a major surgery, that also depends on the age and various other factors, right? So those are some examples. Recovery after a major surgery. In such situations, somebody who has the subject expertise will have to evaluate so many factors and come up with a certain probability. Let's move on to the next point. Point number 6, notations. So the first one is union. We are going to use a symbol for the union. The symbol is a letter U. Or you can write it in words. It's given as or. Almost always you have to do word problems for probability calculations. So when you read carefully, you can see these kinds of technical words, or, between two events. That means we are talking about the union of the two events. So what are the events? We already defined the events. So I will let A be one event in S, where S is the sample space, and I will let B also be another event in the same sample space. Now A union B can be written this way, A U B. This may also be written as A or B. Now this means all the elements found in both sets. That's the union. So we'll look at an example. So my S could be 1, 2, 3, 4, 5, 6, rolling a die experiment. I'm going to let A be the event 1, 3, 5. Received site is an odd number. And I'm going to let B be the event 3, 4, 5. 3, 4, 5, 6, I would say. Okay. Now, what's my A union B? A union B. All the elements found in both sets. I have 1. I don't have 2, therefore I will not write 2. And I have 3. And I have 4. I have 5. I have 6. So that's the union. So the same thing can be written as A or B as well. Okay. Same set. Now this is an example for discrete random variables. We will also look at an example from continuous random variables. Let's say I have sample space is rain, which is 0 to positive infinity. I'm going to define A as the event that 0 to 5-inch rain. And I'm going to define the set B as 4 to 10-inch rain. Right? Then what will be my A union B? I can write A U B, or I can simply write A or B. That set will be what? So 0 to 5 is the first one. And then 4 to 10 is the second one. We said everything should be included in the union. So it should be from 0 to 10. So that's the union. They are written in interval notation. Okay. Now, these are written with closed brackets. Am I required to maintain closed brackets? Well, for mathematical accuracy, I should write it that way. For example, if this end was an open parenthesis, for mathematical accuracy, I should write this also as an open parenthesis. But on the other hand, for statistical calculations, when the random variable is a continuous random variable, the probability of equality doesn't play a role. Probability that your random variable is equal to a given value will always be equal to 0 when your random variable is continuous. So, practically speaking, in terms of statistics, writing down it as an open parenthesis, so close bracket, will not do any harm as long as you're working with a continuous random variable. Of course, the interval notation is used only for continuous random variables. Okay? All right, let's keep that in mind. So that's how we can define the union. Let's move on to the next one, which is the intersection. The intersection between two sets will be written using symbols this way, like a little n. That's one way to write it, or you can write it inverts as and. And like I said earlier, always the probability calculations come from the word problems. So when you read the word problems, carefully look for the keyword and. If so, I'm talking about the intersection of two sets. Alright, so here's the formal definition. I will let A be an event in S. I will let B also be another event in S. So A intersection B, you can write it this way, or if you prefer, you can write it as A and B. Either way is fine. This means only the elements commonly found in both A and B, not in one of them. Okay? Any elements found in both A and B will be included in the set A intersection B. Okay? Only the elements found commonly in both A and B. So we'll do an example. Now here's the example for discrete random variable case. I will let A be 1, 3, 5. And I will let B be the event 3, 4, 5, 6. Okay? Now in this case, A intersection B, or you may write this as A and B, will be equal to what? Well, I can see 3 in both places. So 3 will be an element in the intersection. And other than that, I can only see 5 in both sets. So 3 and 5 will be the only possible elements in A intersection B for this case. So the next part is complement. Pay attention to the spelling. It's complement, P-L-E. The complement of set A is written as A prime, like that. So let's see what we mean by the complement. So I will let S be the sampler space. And A be an event in S. So A prime, or the complement of A, means elements not found in A, but in S. Okay? So I will write it as that. Elements not in A, but found in S. For example, let's say our sample space is 1, 2, 3, 4, 5, 6. I will let A be the event 3, 4, 5. Then what should be my A prime? A prime should consist of the elements not found in A, but found in S. Of course, I don't have 1, 2, and 6. Therefore, A prime should be 1, 2, and 6. Okay. We will also look at an example for the continuous random variables. So I will let S be 0 to positive infinity. And I will define A as the event 0 to 10 inches. So what should be my A prime? Should be from 10 to positive infinity, right? 10 to positive infinity. And for mathematical accuracy, I wrote this as open parentheses because 10 should not be included. But that step is not very critically important for any of the calculations in our stat class. Okay? Because of the same reason that we explained earlier, probability that x is equal to 10 will always be equal to 0 when x is a continuous random variable. Now we have to know how to do some calculations with the probabilities. For those calculations, we have theorems and axioms. So what are the axioms? Axioms are mathematical statements which are accepted as true and correct, but without proof. We are convinced that those statements are correct, so we go ahead and accept. And there's no way to prove them. Those are called basic axioms. On the other hand, the theorems have proofs. So in this section, we will see both axioms and theorems. First, we will see basic axioms of probability under point number 7. Okay, so here's the first basic axiom. This is about the null set. The symbols for the null set are phi, or the curly brackets with no elements inside. So the probability of the null set is equal to 0. That's the first basic axiom, and we don't go for any proof of that. And then the second basic axiom is about the probability of sample space. We know the sample space has the symbol S, and the probability of the sample space is always equal to 1. That's the second basic axiom. And the third basic axiom is I could let A and B be two mutually exclusive events in S. So what are the mutually exclusive events? Mutually exclusive events means there is no intersection between them. Okay, that means intersection is null set. Mutually exclusive means A intersection B is equal to null set. Now, if that's the case, the third basic axiom says the probability of A union B, or in other words, the probability of A or B will be equal to probability of A plus probability of B. That's it. That's a basic axiom. So you have to always remember these three basic axioms. The third one, please remember it with this part. We cannot write this statement unless A and B are mutually exclusive. Okay? Good. So those are the basic axioms, and the basic axioms alone will not be completely enough to figure out most of the probabilities. Especially, you will see events often which are not mutually exclusive. In such cases, how can you find the probabilities? Now that's given by a theorem. That theorem is called the principle of inclusion and exclusion. It's given under point number 8. Let's go to point number 8. Now here's the principle of inclusion and exclusion. We will let S, this is under point number 8, we will let S be the sample space and the sample space of any random variable, and I will let A and B be any two events in S. So they are not necessarily mutually exclusive, okay? So there can be an intersection between A and B. The theorem says the probability of A union B, which you may also write as probability of A or B, is equal to probability of A plus probability of B minus probability of A intersection B. So if you prefer the words rather than the symbols, union and intersection, you can write it as probability of A or B equals probability of A plus probability of B minus probability of A and B. Now you can also see that you can rewrite this term on the left hand side and that term on the right hand side if you want to. And if you do that, you get probability of A intersection B equals probability of A plus probability of B minus probability of A union B. Okay? Or in other words, the same thing can be written as probability of A and B is equal to probability of A plus probability of B minus probability of A or B. Okay, it's the same equation. I just flipped these two terms of that equation. So that's called the principle of inclusion and exclusion. It can be proved because it's a theorem. So would you like to prove it? Well, I will discuss an example of this theorem after showing you how to prove. And if you don't want to know how to prove, which is actually not required for intro statistics at most of the universities, including my university, you can safely skip this part and straight away go into example from this theorem. But right now what I'm going to do is I'm going to show you how to prove this theorem, principle of inclusion and exclusion. I will just leave this first line and erase the rest so that I have some more space. I will draw a Venn diagram for the sample space first. So this is my sample space. And I have two events, A and B. So I will draw two events using Venn diagrams. So this may be the event A, and now here is my event B. So there is an intersection, which means they are not mutually exclusive. So this is the most general case you will almost always have to deal with. Okay? Now I need the probability of A union B. A union B means everything. Well, how can I find the probability of A union B? All of these. Well, I can write all of them as A with that this part of B, correct? A, and with that I will only go for this part of B. We will try to figure out these pieces. Okay? So complete A is shaded in green alone. And this middle part, I will keep some dots in that part. That is A intersection B, correct? So that is A intersection B. Now this part of A, how do you write that part of A? Now I can write this part of A as A intersection the region which does not belong to B. So the region does not belong to B means B prime. That part can be written as that. A intersection B prime. The same way, I can write down this part as B intersection A prime. Because this part belongs to B, but it does not belong to A. Therefore, B intersection A prime should be that shaded part. B intersection A prime. Now, what I need actually is an equation for the probability of A union B, which is this entire piece which is shaded. So, A union B, how can I write that? A union B can be written as two pieces, complete A, with that take this blue shaded part which is B intersection A prime. So I will write it as that. A, with that I need the union of B intersection A prime. Now if you look at these two sets, aren't they mutually exclusive? Well, of course this is A and this part is B intersection A prime. They are mutually exclusive. There is no intersection between those two pieces. Therefore, using the third basic axiom, I can write down the probability of A union B as probability of A plus probability of B intersection A prime. Okay? I will write it as that, since A and B intersection A prime are exclusive. Using the third basic axiom, we can write down probability of A union B equals probability of A plus probability of B intersection A prime. I will label this as number 1. Now I need a way to figure out this part. Now let's look at the event B. Now event B can be written as this piece union this piece. Event B can be written as A intersection B union B intersection A prime. I will write it as that. So the event B can be written as A intersection B union B intersection A prime. Now again, if you look at those two pieces, they also don't have an intersection. They are also mutually exclusive. Therefore, once again, I can use the third basic axiom and write down the probability of B equals probability of A intersection B plus probability of B intersection A prime. So I will write it as that. I will say, since A intersection B and B intersection A prime are exclusive, mutually exclusive. Using third axiom, we can write down probability of B equals probability of A intersection B plus probability of B intersection A prime. Now from this equation, I can subject probability of B intersection A prime and plug it in here. So I will subject probability of B intersection A prime, that guy. That will be equal to probability of B minus probability of A intersection B. I will label this as number 2, and I'm going to plug in number 2 for this space of number 1. Then I get probability of A union B equals, I have PA, probability of event A, plus all this. Okay, probability of B minus probability of A intersection B. Now that's the complete proof of the principle of inclusion and exclusion when you have just two sets. Let's do an example from the principle of inclusion and exclusion. Let's move on to point number 9. So here's problem number 9. Discs of polycarbonate plastic from a supplier are analyzed for high scratch resistance and high shock resistance. So two events are clearly given. So I will define them as A and B. So I will let A be the event of high scratch resistance. And I will let B be the event of high shock resistance. The supplier confirmed that 95% of the discs have high scratch resistance or high shock resistance. That means probability of A or B is equal to 95%, which I will write as 0.95. When tested, 79% of the discs showed high scratch resistance. High scratch resistance, which is the probability of A, is equal to 79%, which means 0.79. And the other part, 86% of the discs showed high shock resistance. High shock resistance is given by B, so probability of B is equal to 0.86. This first probability, you may write it as P A union B as well. This is equal to 0.95. This is preferred mathematically, but if you are a stat student who doesn't like mathematics that much, then you can go for this symbol. Okay, you can just write it as OR. So read the question carefully. You can always figure out those key terms. The question is, what proportion of discs should have high scratch resistance and high shock resistance? That means I need the probability of A and B. Or in other words, what I need is the probability of A intersection B. That means I need to use the principle of inclusion and exclusion, which says probability of A and B equals, well, we have it in two forms, right? One is probability of A or B equals, the other form is probability of A and B equals. So for this one, what we need is the second form, which will be equal to PA plus PB minus PA or B. Okay? So I just have to plug in these values and get the answer. So PA equals 0.79 plus PB equals 0.86. A or B is equal to 0.95, and you can simplify that and get the answer. Let's move on to the next point, independence of two events. Point number 10, independence of two events. Now, independence of two events is different from mutual exclusive events. Mutually exclusive means there is no intersection between A and B. Mutually independent means something else. Okay? Mutually independent means the probability of one event does not affect the probability of the other event. Okay. So we say if A and B are independent, I will say, which means the probability of A does not affect the probability of B. Now, if that's the case, then there is one specific equation that holds true. That equation is the probability of A intersection B will be equal to probability of A times probability of B. You may write the left-hand side in words as well. So it's probability of A and B. This will be equal to probability of A times probability of B. That is only if A and B are independent. Now, how does this equation hold true? Well, that cannot be explained at this point. But in the next chapter, we are going to talk about something called the conditional probability. In that section, I will explain how does this equation hold true when A and B are independent. Okay? So at this point of time, just accept this equation as it is for independent events A and B. So we can use this equation for two purposes basically. The first purpose is if I know the probabilities of A and B events, then I can multiply the two probabilities, and if I also know the probability of A intersection B, I can compare that probability with the previous multiplication. If they are equal to each other, we can conclude that the events A and B are independent. We can also do the inverse calculation. If in the question given that A and B are independent, in that case, we can straight away use this equation. So if A and B are given as independent in the question, it practically means we don't know one of these three pieces. Okay? And you have to find the missing piece. Since it's given in the question that A and B are independent, we can use this equation. Plug in the given two values, and the third value can be simplified using the equation. Okay? Cool. All right, I'll come to point number 11 in a minute. We will go to point number 12 straight away. This is regarding the previous question that we discussed regarding the scratch resistance and shock resistance. Are scratch resistance and shock resistance independent? Now we have to answer that question. We calculated earlier the probability of scratch resistance and shock resistance. Okay, that was the probability of A and B. It was calculated and it was actually equal to, if you simplify those numbers, you can see that it will be equal to 0.7. Also in that question, we were given the probability of scratch resistance and probability of shock resistance, high scratch resistance and high shock resistance. So the probability of A, I think we defined event A as high scratch resistance. So the probability of A was given as 0.79. And probability of B, which was the high shock resistance. The probability of B was given as 0.86. Now our question is whether the events A and B are independent. High shock resistance and high stress resistance, are they independent? So what I'm going to do is, I'm going to multiply these two values and see if that will be equal to 0.7. If so, if that's equal to 0.7, we can conclude safely that A and B are independent. So I will find PA times PB, which is 0.79 times 0.86, which is equal to 0.6794. Now that's not equal to 0.7. Therefore, we can conclude that the events A and B are not independent. Okay. All right, let's go back to problem number 11. Please read and see if you can answer. So the problem 11 says, a company delivers 90% of its online orders on time. A student ordered a laptop. Later that day, he decided to enroll in statistics. Therefore, he ordered a statistical calculator as well. The two orders are separate orders. Therefore, they can be considered independent orders. What's the probability that both laptop and calculator will be delivered on time? What's the probability that at least one of them, that means laptop or calculator, will be delivered on time? So I will define the two events. I will let A be the event that laptop delivered on time, and I will let B be the event that the calculator delivered on time. Now the probabilities of A and B are given, right? In the first line it says the company delivers 90% of its online orders on time. So it should deliver the laptop as well on time with that same probability of 0.9, and probability of B should also be equal to 0.9. The orders are independent. Now I need to find the probability that both laptop and calculator will be delivered on time. Okay? That means I need to find probability of A and B. Or in mathematical symbols, this is the probability of A intersection B. This is what I need. Now that will be equal to probability of A times probability of B, because A and B are independent. Please remember, if it's not explicitly given as independent, we cannot write down probability of A intersection B equals probability of A times probability of B. But it's given as independent, therefore I can write this down as PA times PB. I will write down the reason. This is because A and B are independent. It's given in the question. So we can plug in those two values, which is 0.9 times 0.9. So the simplification is 0.81. And as the next part of the question, what's the probability that at least one of them, that means laptop or calculator, will be delivered on time? Once again, we have the keyword or. That means I need to find the probability of A or B. Or in other words, what I need is the probability of A union B. So you can use whichever the format you are comfortable with. So A or B, how can I find that? To find that, I need to use the principle of inclusion and exclusion, which is this probability is equal to probability of A plus probability of B minus probability of intersection, or in other words, A and B. That's the first form of the principle of inclusion and exclusion. So I will plug in these values. PA equals 0.9, PB is also equal to 0.9, minus PA and B is equal to 0.81. right? So we can simplify that and obtain the answer. I think this simplifies to 0.99. All right, so that's how we can answer question number 11. Let's move on to the last example given, which is problem number 13. So the problem 13 says the diameter of a bearing should follow a normal distribution with a mean of 0.2500 inches and a standard deviation of 0.0005 inches. The surface roughness should follow a uniform distribution from 32 RMS to 64 RMS. Assume that the diameter and surface roughness are independent of one another. As per the specifications, type A bearings are classified as bearings with diameters between 0.2493 inches and 0.2507 inches and surface roughness lesser than 48 RMS. What proportion of bearings is classified as type A? There are two random variables very clearly given. So the first random variable is the diameter of a bearing. So I will let x be the diameter. That's the first random variable given. Now this x follows a normal distribution. We can write down using the standard notations, we know them. With a mean of 0.2500 and a standard deviation of 0.0005, which means variance should be 0.0005 squared. So that's that random variable. And then surface roughness, that's the other random variable. The surface roughness follows a uniform distribution from 32 to 64. So I will define y as the surface roughness. Now y follows a uniform distribution from 32 to 64. And then we have to define the two events. So two events are defined for type A. And also given that diameter and surface roughness are independent of one another. Okay? X and Y are independent. So this will be very important. And then we have two events defined for type A bearings. So type A is classified this way. Diameter should be between 0.2493 and 0.2507. Okay. So diameter is x, so x should be between those two given values. 0.2493 and 0.2507. So this is one event actually. X is going to be existing between those two values. Well, the classification also has already used the letter A. So I will use a different letter for the first event. I will label this as event, let's say C. Okay. And the surface roughness should be lesser than 48. That means the random variable y should be lesser than 48. So I will define this guy as the event D. And I can find these probabilities quite easily because I know the distributions. And again, I can write down the equal signs without any problem because x and y are both continuous random variables. These distributions are continuous distributions. Okay? Good. Now x and y are independent. Therefore, eventually C and D should also be independent. Okay? Because C is written in terms of x and D is written in terms of y, so they should be independent naturally. Now I need to find the proportion that's classified as type A. That means basically I need to find probability of C and D. Or in other words, what I need is probability C intersection D. So this will be equal to probability of C times probability of D. So I need to find these two probabilities respectively. Okay? So let's find probability of C. So C is about this, and X follows the normal distribution. So this is the distribution of X. It's a normal distribution. And it should be centered at 0.2500. The two given values are 0.2493, which should be on the left, and the other value is on the right, which is 0.2507. So what I need is this shaded area. So how do you find it? You already know how to find it. You have to go to distributions, select normal CDF. The lower limit is 0.2493. The upper limit is 0.2507. Mu equals 0.25. Sigma equals 0.0005. That's all. And then you can get the answer.
Here's our TI-84CE Plus calculator. I have to access distributions, which is by pressing second and variables. That's where I have distributions. And select number 2, normal CDF, hit enter. The lower limit is 0.2493. And the upper limit is 0.2507. Mu is equal to 0.2500 and sigma is equal to 0.3005. That's all I need, and select paste, hit enter, and hit enter again. We get 0.8385 approximately.
The answer I got as the probability of C is 0.8385 approximately. And the same way I can find the probability of D. Now D follows a uniform distribution between these two values. So the distribution of y, the random variable y, is a uniform distribution 32 to 64. That means a rectangular distribution. So what should be this vertical height? That vertical height should be 1 over this length, so that the product of these two sides will be equal to 1. So this length is 64 minus 32, which is also 32. So the vertical height should be 1 over that, 1 over 32. What I need for probability of D is that y is lesser than 48. So 48 will be somewhere here. Lesser than that, which means area to the left from that point. Now it's again a rectangle. This side times this height will be the area, which is the probability I need. So probability of D can be easily found from that. So this side will be 48 minus 32, which is 16. That times the vertical height, which is 1 over 32. So they will be simplified to 16 over 32, which is 0.5. And then I can easily plug in those two values in this equation and find the required probability, C and D. Okay? So probability of C is equal to 0.8385. That times probability of D, which is 0.5. Okay? So this will be simplified to 0.41925. Okay? So that's the proportion classified as type A. Alright, so that's basically it about the simple probabilities under chapter number 12. You need a solid understanding of these concepts to move into the next chapter, which will be chapter 13, conditional probability. Alright, thanks.